this one a little bit more interesting. We're going to talk about the launch window, and that is the one going to show you how the people consider to define their launching time. So if you have watching the movies and TVs, and basically you can see they always have a countdown and to launch, right? And how they determine it. Here I can provide you a little bit more, I would say rough, but it's the right direction of the thinking. The whole idea is this, and before I proceed, the whole idea is this. If we wish to launch something to the right, to a designed orbit, and say the first one you need to design your orbit. So once you have an orbit is designed, so basically is the step one is design the orbit, and depends on your applications, and you need to define the orbit in certain ways, say inclination in certain degrees, and or is the accessing node at where, and then whatever, and the size, etc. Okay, so that means here the 6 orbital elements are chosen already at this moment. So once you define your orbit, then you have the second step is to select the launching site. So which means which city and which launching site will be available to meet these missions. And not everywhere on Earth is appropriate to launch the satellite or missile to any desired the orbits. No, they have a lot of constraint there. And I'm going to talk about in a few minutes. So once you select the launching site, the first one is you select the launch time. Okay, you have to be precise, otherwise you're going to consume the fuel, because once you put your things on the satellites into the space, if that is not on the orbit, what will be the next step you can do? Do the orbit transfer, right? If the things in the space already, and if not on the desired orbit, then the remaining things we can do at ground is to we simply send the command to the satellites and asking using his own fuel to do the orbit transfer. And the orbit transfer can be in plane and can be out of plane. We already have those kind of techniques already. Okay, so it's okay. So that is the whole procedures. And assuming here we assume for our illustrations, assume we have the selected given desired orbit already. Okay, so that is our information. So let me draw that kind of orbit in terms of the Earth sphere. Okay, so so right now the orbit in space is if this is the Earth, and this is orbit, something like this one. And here right now I'm going to draw is the projections of the orbit onto the Earth's surface. So that line can be drawn like this. A little bit challenging. Let me define the coordinate systems first. So define this is I, this is J, K coordinate systems. And let me define the equatorial plane. So this, let me write to the sides because I have a lot of things to write. So this one. So here is the 1/8 of this Earth sphere and the projections of the orbits onto the Earth's surface, and let me put into like this, okay? And we see the curve like this because the Earth's surface is spherical. So once we project it, once we see, it will be something like this one. And so this is the intersections of the orbits to the equatorial plane. So basically this is the node, one of the node. So for example, assuming say the satellite is moving in this direction, so this is the, we call the node, descending node, ascending node. And on the back side, and back line going down, that point is called the descending node. So that's the terminology we use. Okay. In the meantime, excuse me. In the meantime, the Earth is rotating, and the projections of the orbits onto the Earth's surface basically, once we define the orbit, this orbit is fixed in space. So right now the Earth is rotating. So basically here we can see, if you have seen watching the movie, they have the control centers, and once they display they call the ground tracking. The ground tracking is to display the spherical shape of the Earth's surface into the two-dimensional, and one way you see this kind of ground tracking curve, something like this one, right? And so basically this one, each of the curves representing is the projection of the orbit into, say, from here to here is 360 degrees of the Earth. And at the same location from here to here, simply that represent is one cycle of the satellite and passing through. So basically this is one cycle that is a period multiplied with the Earth's rotation speed, and that defines the distance. That means between each cycle and the drifting of the projections onto the Earth's surface, something like this one. Okay, and now we come to here. The projection of the orbit is fixed, and which is we call the ground tracking curve. And now we want to determine what is the launching site here. The launching site is determined by this. In the purpose of using the minimum fuel in launching, the right moment and the right side is such that the projection of the orbit just passing through the site you like to launch. So for example, say if Fairbanks is here, and to the certain moment due to the Earth's rotation, the Fairbanks will just align intersection with the projection of the curve of the orbit. So this is the best. This is the best one, and you can see maybe the anchorage is here. The anchorage could fit or could not fit. So it will depend. And say, for example, say. Let me make one example here. So maybe say any site in the northern area. So for this one, you can see this city won't be able to intersect with this one. So if we would choose this site as the launching, then definitely once the objects in the space, we have to do a lot with the orbit transfer to get that one onto here. Okay, so that is the concept. So now under these situations, then we want to select the launching time. The launching time can be determined is this. Assuming at this moment, this is a good moment for launch, and assuming, so basically here is since is the right at this moment, the orbit is right on the top of the, say, Fairbanks. Okay, and say assuming we take the launch, it's only take no time, say 1 second, the things will be up to there, so hopefully that will be aligned to you. But usually launching time is take about 6 minutes to 10 minutes. So during the flight, the orbit has been drifted a little bit, but that's okay, a little bit drifting, that won't take too much fuel. Okay, but here we talk about the concept. So here, let me define. So here is the longitude of the site. Okay, so this is the theta, LST. So under these situations, as long as we can find the theta LST, that is the right moment of the launching time. We can always convert the theta LST into this Earth time. Okay, so that is one way to determine the theta LST. And let me do the calculations here a little bit more. So we're going to give a few informations. So from here, we know this is intersections. This is, for example, this is the node. And so we know, let me draw a few line here. So this is the longitude to node here. So we know this angle is omega, right? Part of the orbital element. And let me define this angle. It's delta, okay? And this angle, that means the angle between the orbits to the equatorial plane. If you remember, that is our inclination angle I. So here I and omega are two orbital elements. So here we have A, we have E, omega, I, omega, and the other one is nu, right? So right now we have been using the two already. And here. And furthermore, we can define is the angle here. So we measure the angle here. This is the azimuth angle of the orbit. And also, this is the longitude. So, sorry, latitude. So, measure from the equatorial plane to the site, that is L. That is our latitude of the site. So, from here you can see all of those angles. We have quite a few. Few of the angles are measured in the IZ plane, and few other angles are actually measured have the elevation. Okay, so here we can utilize our information for spherical, and the deformation is this. We using, they call this spherical trigonometry. METR trigonometry. Okay, so here we can calculate data, and that one directly give you the formula here times cotangent I. So therefore, from here we can determine delta. Okay. So therefore, from here you can see theta LST at launching simply will be equal to, by reading the graph, is omega. That is the one of the orbital element and plus delta. Okay. So in this way we can the launching we can determine, and this one, the launching, basically this information you see, this information involved is basically that is theta GST plus delta T times omega of the Earth. So from here you can determine what is the time, exactly the time you have to launch the satellites. Okay, simply that is from this formula here. Okay. And assuming the Earth is rotating like this, and are you able to see if for certain reasons, say due to the weather conditions, we miss this launching, do we have other options? Yes, we're simply looking for, say, given this situation, we're simply looking for the next moment when the city, due to rotation, hit the projection of the orbit. So which means we keep rotating along with the Earth. So next moment will be here, right? And that moment is what moment? And let me put into the calculation here. So if this is the equatorial plane, we're looking into the North Pole is here. So basically this is the North Pole and out the South Pole is on the other side of the board. So this is equatorial plane. Okay, so I try to do that kind of the way. So here, for example, here is our y-axis and z-axis. Okay, and let me put that number here. So this is the omega. Okay, and we missed the window. So at this moment, so this is the delta. And this is one node here. So basically, this is a line of the nodes. Okay, due to symmetry of the orbit. So say at this moment, if right now need a little bit kind of imagination, this is the perigee. Okay, so for example, this is the perigee here. So basically, respect to the long axis, the perigee, basically the orbits become kind of symmetric. So under these situations, we have another way we will hit is here. So that means to this moment, and the orbit will become like this. So this is the delta. So the next moment we will continue to proceed will be this angle. So we're simply waiting for the rotation of the Earth to bring us to passing through this angle. Then we will hit the second launching opportunity. And this angle actually is 180 degrees minus 2 delta, right? So again, if we would miss this launching time, then the next moment would be once the Earth rotating that much angle to hit another intersection here. And that angle is that much. So therefore, the second launching time will be theta LST will be equal to this omega plus delta and plus additional rotation. That additional rotation is this one. So that is the omega plus delta and plus additional rotation, 180 minus 2 delta. Okay, so basically in Earth, they're rotating from here to here, that is 180 minus delta. So that will be equal to omega plus 180 minus delta. So again, this one involve, this one basically theta GMT plus delta times omega of the rotation of the Earth. So from here, this is the angle we calculated. And from here, we can determine the next launching time. And on Earth, in theory, we only have twice a day. If you have defined your orbits, we have selected only twice. If you miss and you wait for the next one, otherwise you have to wait for the next day. Okay. And another, this is the one, so basically here we know how to select the launching time. And of course, and this is a basic assumption that we assume that, and the city just intersect with the projection of the orbit, and assuming the launching will take no time to bring the satellites to space, but usually it takes about a few minutes. So during the few minutes of the flight in launching, the drifting, the orbit may be drifted a little bit, but that's okay. That little drifting is okay. And also from this concept, we can further to fine tuning our calculation to exactly consider the launching period and launching process to get the things to the desired orbit. The second important thing, I want to take this angle and give you another thinking is this. And again, using spherical trigonometry, we have the second relation is cosine I equal to sine Aramus and times cosine L. Okay, so what is these relations? So this relation, this I is the inclinations of orbit, and this is the latitude of the launching site. Due to the geometry, this relation must be satisfied. So from here you can see, because sine AZ is always less than 1, so which means, let me say, cosine I divided by cosine L equal to sine AZ, which is less than 1. So from this relation, you can see the smaller the angle I, the larger the IZ. So from this relation, we can see the inclination is always larger than or equal to L. What this means? This is a very important information. This one is regarding how do we select the launching site. So that's the reason why the French, they have occupied island nearby the orbital equators there, and they call the low latitude the launching site. And why Russians, they before in their union, they have a launching site more toward the southern side. And you barely on the Earth see launching site in the high latitude. The reason why is this. The inclinations must be greater than, the angle must be greater than the latitude. So say if this is the Earth, say here we have a site and the longitude say equal to 55 degrees. The other one compared to is this L equal to 10 degrees. Let me ask, this is a launching site A, this is site B. Which site will give us more flexibility to design the orbit? B, because this one gives us more space, degree freedom to choose I. If we're launching from here, then due to the geometry, I must be greater than 55 degrees, then basically you have defined your orbit, your inclination must be greater than this angle. So you're losing other opportunity of, say, probing any site lower than, say, 0 degrees. If you have a launching site at just on the equators, holy cow, you have a capability of designing orbits which cover everywhere on the Earth. Okay, so consider this. So basically using the kind of information. Again, here for me, I never learned this before, and I simply copy from from the textbook. But I know the result, the information is interesting. So using the two things, I simply in the answer more precisely how to select the launching site. And on Earth, most of the launching sites, they have a latitude that is lower than 30 degrees. Say in Canada, Kennedy Space Centers, I think their latitude is about 30 something, about that degrees. And in China, they have two very famous, and they basically launching for satellites for missiles. Okay, so usually they have the degree is about 35 or below. And if you have an interest, you can look up the internet and you can see a lot of information. Okay, so in this way, using these sections, we finished our chapter 3. So.